In this video, we will talk about how to solve a special case of the transportation problem called the assignment problem using the Hungarian method. This is a typical assignment problem. A company is relocating 4 employees to 4 cities. Each employee must be moved to only one city. Each city must receive only one employee. This is the relocation cost matrix. For example, if employee 1 is relocated to city 1, the cost is $14,000. If the employee is relocated to city 2, the cost is $5,000, and so on. The objective is to minimize the total relocation cost. For the decision variable, we define xij is equal to 1 if employee I is relocated to city j. Xij is equal to 0 if employee I is not relocated to city j. The objective function is the total cost. For example, if employee 1 is relocated to city 1, x11 is equal to 1, and its contribution to the total cost will be 14 times 1. If employee 1 is not relocated to city 1, x11 is equal to 0, and its contribution to the total cost will be 0. We need to sum up the cost of all 4 employees. As for the constraints, each employee must be moved to only one city. The sum of relocating employee 1 to city 1, city 2, city 3, and city 4 should be exactly 1. We have this constraint for employees 2, 3, and 4 as well. Each city must receive only one employee. The sum of relocating employees 1, 2, 3, and 4 to city 1 should be exactly 1. We have this constraint for cities 2, 3, and 4 as well. This is the complete problem formulation. The assignment problem is a special case of the balanced transportation problem. The objective function is the sum of the cost matrix times the decision variables. The sum of each row is equal to the supply, which is the total number of available employees. The sum of each column is equal to the demand, which is the total number of cities. The total supply is equal to the total demand, 4 is equal to 4. Therefore, we can try to use the transportation simplex method to solve the problem. We use the minimum cost method to find the initial basic feasible solution. We find that basic variables have many zeros in the transportation tableau, so we know that the problem is highly degenerate and the transportation simplex method is inefficient to solve this type of problems. And in some extreme cases, it may be trapped in a cycle and will never find the optimal solution. Therefore, we will introduce another more efficient method to solve the assignment problem. It's called the Hungarian method. The assignment problem has a square cost matrix. It has the same number of rows and columns. There are 3 steps involved when solving the assignment problem using the Hungarian method. Step 1. In the m row by m column cost matrix, find the minimum cost in each row. Subtract each cost by the minimum cost in each row. In the new matrix, find the minimum cost in each column. Subtract each cost by the minimum cost in each column. Step 2. Draw the minimum number of row or column lines to cover all zeros. If the number of lines is equal to m, an optimal solution is available among the covered zeros. If the number of lines is less than m, go to step 3. In step 3, find the smallest non-zero element that is not covered by the lines drawn in step 2. Call this smallest element k. Subtract k from each element that is not covered and add k to each element that is covered by 2 lines. Then return to step 2. Now let's check this cost matrix of the relocation assignment problem. In step 1, we find the minimum cost in each row. It is 5 in the first row, 2 in the second row, and so on. Let's subtract each cost by the minimum cost in each row. 14 will be changed to 9, 5 will be changed to 0, and so on. This is a new matrix. Now we find the minimum cost in each column. It's 0 in the first column, 0 in the second column, 0 in the third column, and 2 in the last column. Subtract each cost by the minimum cost in each column. This is the updated cost matrix. In step 2, we draw the minimum number of row or column lines to cover all zeros. We draw a horizontal line to cover 2 zeros in this row. Draw a vertical line to cover these 2 zeros. For the last zero, we can draw a horizontal line or a vertical line. We randomly choose to draw a horizontal line. Therefore, we need a minimum of 3 lines to cover all the zeros. 3 is less than n, which is 4. So we need to go to step 3. Step 3, let's find the smallest non-zero element that is not covered by the lines. The smallest is 1. We give it to k. Then we subtract k from each cell that is not covered, and then add k to each cell that is covered twice. This is the updated cost matrix. Then we return to step 2 and find the minimum number of lines to cover all the zeros. In this case, we need at least 4 lines, which is equal to n. Therefore, the optimal solution is available among the covered zeros. Let's rewrite this matrix and only keep the cells of zeros. Then we change all the zeros to ones and check the row and column constraints. Every employee must be relocated to only one city, so the sum of each row should be 1. Each city must receive only one employee, so the sum of each column should be 1. For the first column, the sum should be equal to 1, but now we have 2. We don't know which one should be removed. For the second column, the sum is exactly 1, so we know this cell must be 1. Similarly, for the third column, the sum is exactly 1, so we know this cell must be 1 as well. For the last column, the sum should be equal to 1. We can't decide which one should be removed yet. Now let's check the row constraints. For the first row, the sum should be equal to 1. We know this must be 1, so this should be changed to 0. For the second row, we cannot decide which one should be removed. For the third row, this is already 1 and the constraint is satisfied. For the last row, for the sum to be 1, we know this cell must be 1. Now let's check the column constraints again. For the first column, we know this must be 1, so this cell must be 0. The second column and the third column are still the same. For the last column, we know this is 0, so this must be 1. This is the optimal solution. We plug in the values of the objective function z is equal to 15. Okay, this is how to formulate and solve the assignment problem using the Hungarian method. Thank you for watching.